All right, we're going to talk about a different data structure today, actually two data structures, which are called stacks and queues. And they're very similar to each other. There's really only one difference between a stack and a queue. And so we're going to start by talking about stacks, and we'll develop that and look at some implementation details, and we'll look at stacks as abstract data types. And then when we're done with that, we'll go back and we'll look at queues. And everything we did with stacks will pretty much apply with just, sort of one minor change. But let's start with stacks. So what's the idea of a stack? It's something that we actually encounter in our daily life, and it can be thought of as literally a stack. So suppose I want to store a number of things on my desk. So I have a cell phone, and I can put that cell phone down. And now I want to store the instructions for a cookie press. So I put that on top of the cell phone, right? So it's sitting up there. And now I want to store, a little 3D printed plastic box. So I put that on top of the cookie press instructions, which is on top of the cell phone. I'm building a stack, right? It's literally a pile of things that are sitting on my desk. And one of the rules of a stack is you can only add things to the top of the stack, and you can only remove things from the top of the stack. So I could remove this little 3D printed box, or I could put something else on top of that. But I'm not allowed, for example, to try to remove the phone from inside this stack. The only way I can get to the phone would be to remove what's at the top of the stack, and then remove what's at the top of the stack. And then when this phone is at the top of the stack, I can take it off the stack. And so now, maybe I want to put a mouse pad on my stack, and maybe my cookie press instructions, and then a phone, and then maybe a highlighter, right? So now I have four things on my stack. And again, I can't get to the mouse pad or the cookie press instructions or the cell phone until each of those things is at the top of the stack. I'm only allowed to access what's at the top. And I'm only allowed to put things on the top. I can't take this piece of paper and insert it in the middle. I can only put it on the top. That's really all there is to the notion of a stack. It's a collection of information stored in a computer with this kind of peculiar property that we always add to the top of the stack, and we always remove from the top of the stack. So we can picture our stack kind of looking like this. It's kind of a one-way container, right? And we can add things by putting them in like this, and we can remove things by pulling them off from the top. So when we add something to the stack, we call that a push, and when we remove from the stack, we call it a pop. So we can initialize our stack, and when we initialize it, we basically just get an empty stack. It's a container with the capacity to hold things that are pushed, or to let us retrieve things by popping, but initially the stack is empty. And so we can think of, as an abstract data type, we talked about this with linked lists, one of our functions for interfacing with a stack would be an initialize function that says, hey, let me create an empty stack. We also have a push function, which lets us push some piece of data. So it might be a stack of integers or strings, or binary data of some sort, or everyday objects. But whatever type of data is stored in our stack, we have a function for pushing onto our stack, and we also have a pop function. And pop doesn't need an argument, but it returns a piece of data that's been popped off. And that's a pretty complete set of functions we would need to interact with a stack. We're going to add one or two more. But for manipulating the stack, those are the main things we need. A way to initialize it, and then basically push and pop. And so if we wanted to implement this on paper, we could do something like this. Let's suppose we initialize a stack, and then we push a 10, and we push a 50, and we push a 30. So we could imagine that 10 coming right here at the bottom of the stack. It's the only thing on there. And then we push a 50, and then we push a 30. So at this point, if I said pop, it would pop that 30 off of the stack. So if I say pop, that returns a 30, and this, gets removed from the stack. So now if I say push a 60, that 60 takes the place of the 30, but it basically sits on top of the 50 and the 10. So our stack would look like a 10, a 50, and a 60. We don't actually have a hole here where the 30 was. So it would look more like, 10, 50, and a 60 would be right here. And that's what a stack does, right? Add to the top, remove from the top. And if I say pop, that's going to remove the 60. And if I say pop, that's going to remove the 50. And if I say pop, that's going to remove the 10. And we're back to our empty stack. So there's an error condition that can happen when our stack is empty. If we say pop and there's nothing on our stack, there's nothing reasonable we can return, right? If there's a cell phone on my stack and I say pop, I can give you the cell phone. But if the stack is empty and I say, hey, pop something off the stack, well, there's nothing here to grab, right? So that's an error condition. And if we try to pop, that's called a stack underflow. And that comes from popping from an empty stack. The other thing that can happen, if you've ever done this, if you started piling things up on your desk, you can pile them up so high that eventually you can't put anything else on the stack. And if you put one more thing on there, the whole pile falls over or something like that. There's a limit to how many things we can push on the stack. So our stack can become full, and so push something when stack is full. That gives us another error, which is called a stack overflow. So we might want two other routines in here. We might want a routine called isEmpty, and another one called isFull. And isEmpty will tell us is the stack empty, so we know not to pop. isFull will tell us is the stack full, so we know not to push. And that is a very comprehensive set of functions to interface with an abstract stack. Alright, so that's a stack as an abstract data type. Let's look at implementation of a stack, so the specific ways we can make a stack work inside a computer. And we've got a pair of options for doing that. The easiest way with what we know so far is to use a linked list. So suppose we have a linked list. Well, our initialize function is just the plain old init that we do for our linked list. But what do push and pop look like? So push some piece of data n, insert n at the start of the list. And pop, just remove the node that's at the start of the list. So we actually already did this. We already implemented a stack using a linked list without using those terms, right? When we said let's just insert at the beginning of a list, we started with a sentinel node. And when we said add a 10, we put that 10 right here. When we said add a 20, we sandwiched a 20 in the beginning. And when we said add a 30, we put the 30 in front of the 20. And after adding 10, 20, and 30, this is what our list looked like. So that the thing at the beginning of the list was the 30, 20, 10. And then if we pop, we just remove the thing in the front. So popping once will give us a 30, and then a 20, and a 10. isEmpty. We can tell the list is empty by saying if sentinel next equal to null. If the sentinel is not pointing to anything, the stack's empty. What about the stack being full, though? When would a stack implemented as a linked list be full? Well, really, it would only be full if there was no space left in the computer to allocate another node. Because our structure is just a linked list. If we want to add a new node, if we want to push something new onto the stack, we just allocate a new struct node, set the data field to our new value, and sandwich it into the beginning of the list. The only thing that can go wrong is when we do the malloc statement to allocate a new struct node. Malloc might return a null saying, hey, we're out of memory. And that's pretty rare. That's usually a result of some kind of error, like something running away that's allocating memory and not freeing it, an exit condition that's not formed correctly or something like that. It's a very unusual condition. So for a linked list implementation, we probably would not have an isFull routine, because it's hard to meaningfully tell that your machine is out of memory, because usually everything is failing at that point anyway. But isEmpty is definitely useful, and it's really just seeing if the linked list itself is empty. So that's one way to build a stack, is by using a linked list. But there's another approach, which is to use an array. And this is kind of the more conventional way to think about a linked list. And it takes a little more work. We need a few more pieces in here. So let's make an array. Let's suppose we have a stack of integers. So I could make an array. I'll just call it stack. Maybe I'll make it 100 elements long. And the idea is we have these different locations in the memory, and we can store our data anywhere that we want in here. So we could, start off by saying, let's put our first piece of data down here at index 99, and then the next piece of data will go at 98, and then 97, and so on. And that would, kind of match our picture of things being stacked up, where gravity, pushes things down in this direction. But implementation-wise, it's a little easier if we sort of turn things on their head and we think of our stack as beginning up here and growing in this direction. So the first thing we're going to store in our stack is going to go at location 0. And after we've pushed something here, the next thing will get stored at location 1, and so on. And so we need a variable to record the index where we're going to store our next piece of data. And we usually call that SP. And we call that the stack pointer. So it points to, where in our stack we're going to store our information. So I'll put a comment here. This is where next push is stored. Alright, so if we want to say push n, all we have to say is stack bracket sp equals n, sp equals sp plus 1. That's our whole push function. So if you push a 10, we'll put the 10 right there. SP was a 0, now it becomes a 1. If you say push a 20, we'll store the 20 at index 1, and we'll increment the stack pointer to 2. And now if you push a 50, we'll store the 50 at stack bracket 2, and we'll increment the stack pointer. So the stack pointer always shows where the next thing is going to be pushed, and it's always one more than the last thing that was pushed. So our pop function should be something like this. SP equals SP minus 1, return stack bracket SP. So if I say pop, I'll decrement my stack pointer and I'll return the value 50. And if I say pop again, I'll decrement the stack pointer and I'll return the value 20. And if I say pop again, I'll decrement the stack pointer to a 0 and I'll return the value 10. So push and pop just write to and read from this array, and our stack pointer gets adjusted so that we can remember, hey, where's the next push going to happen? Where was the last push done? I.e., where should the next pop be taken from? Something interesting to note in here. When I said pop and I popped off the 50, we said return stack bracket 2. We changed the stack pointer to here. But this 50, this is still sitting in the memory of our machine. This is still sitting in the array. Our stack pointer was adjusted to be a 2, so we know that there's only 2 things on the stack, but that 50 is still there. Popping does not actually remove the thing you popped from memory. It just reads it from memory, and it adjusts our stack pointer so that we can reuse that location, but it doesn't remove it. In fact, there's no way to remove something from memory. You could write something else in its place, and if you were security minded, you might, when you pop, change the value here, write it out as a 0 or something like that. But if you just do a strict pop like this, the value that you popped is still in memory. And that's important to keep in mind sometimes, because the stack is where we store local variables in C programs. And if you have a local variable with sensitive information in it, when you exit from your function, those values get popped off the stack while they're still sitting in memory, unless you do something specifically to overwrite their values. So, some security notions to keep in mind. All right, we know that popping can fill us up, can underflow the stack, right? Right now the stack pointer is 0, we popped off the 10. If we tried to pop, our stack pointer would go negative, and we'd be trying to index our stack with a negative index. That's an error condition. So is empty, our stack is empty if stack pointer equals 0. And is full, well, if we set our stack pointer to 99 and we push, we're going to store our data right here. That's fine. Our stack pointer will get incremented to 100. But at that point, our stack is full. So it's full if stack pointer equals 100, or, whatever the dimensions of our stack array were. So very easy to tell if the stack's empty or full. It's empty if the stack pointer is 0. It's full if the stack pointer is whatever the capacity of our stack array is. So stack pointer tells where the next push is stored. It also tells us how many things are on our stack. Right after we push 10, 20, 50, stack pointer was equal to 3 because we had 1, 2, 3 things. Empty stack pointer is 0 because we have 0 things. And when it's full, stack pointer is 100 because we have 100 things on the stack, and our array can only hold 100 things, so it's completely full. So before we push, we want to see if we're full. Before we pop, we want to see if we're empty. All right, one more concept to think about with stacks. This is more of an abstract data type notion. This behavior of stacks that, the first thing you put on the stack is going to be the last thing that you remove. I put this 10 in here, 50, 30, 60. The first thing to be removed is the 60. Right? The last thing I put in is the first thing to come out. So this is sometimes called a LIFO, which means last in, first out. The last thing I put on my stack, that's the first thing that gets removed from the stack. And a LIFO is a characteristic of stacks. It's how we can tell a data structure is a stack, because the last thing we put in is the first thing that we take out. Also, the first thing you put in is the last thing you take out, so you could call them a FILO, but nobody does. Call them LIFOs, last in, first out. This is the last thing I put on my stack was a 70. That'll be the first thing that gets popped, right? Unless, I put an 80 on top of that. Now the last thing I put in was an 80. That'll be the first thing that gets popped. So stacks are associated with LIFOs. All right, so there's a second data structure that's closely related to stacks, but it's called a queue. And queue is just a fancy word for a line. So we can think of a queue as looking like this. And it's similar to a stack. A stack we drew up and down. I'll draw this side to side. The thing with a stack was you inserted and removed from the same end of this container. With a queue, we're going to insert in one end and we're going to remove from the other. And there's some terminology here that we want to keep absolutely clear. We remove from the head of the queue and we insert at the tail of the queue. and those are, you know, kind of random definitions, but they are very consistent, and we'll be really consistent about these. So put those down on your note sheets, put them in your comments or your code, commit them to memory when you can. Insert at the tail, remove from the head. All right, so that's how we identify the two ends of the queue. And so if we do something like, you know, insert a 40, that's going to get inserted here, and we can picture it, you know, moving through the queue, going all the way up to the head. If we insert a 20, that's going to go in at the tail and move as far through this queue as it can. And then if we insert a 100, that's going to go into the tail and move as far through this queue as we can. And now our queue has 3 things in it. The first thing that we inserted, this 40, that's the thing that's waiting to be removed. So if I say remove, then this 40 will come out of the queue, and the 100 and the 20 will move down, and the 20 will be the head of the queue. So the second thing we inserted is the second thing that we'll remove. So unlike a stack, which is LIFO, this is called a FIFO, which means first in, first out. So the first thing you put into your queue is the first thing that's going to come out of the queue. And this is just like, you know, a line. Anytime you line up for something to get into a movie theater or a club, or trying to get to the cashier in a line at the grocery store, right? That's what a queue is. And people come into, you know, the back of the queue, and you move as far down the line as possible. And whoever's at the front of the line, they're the ones that are, you know, walking into the door or getting their groceries rung up or whatever. And when they're done, and they're gone, whoever was the second place in the line now moves up to the first place. So it's another notion that we're familiar with in everyday life, this idea of lining up. That's all that a queue is. And in terms of interacting with this in software, we have, you know, a small set of routines that we can use to define an abstract queue. So there's some sort of initialization to, you know, set things up. There's an insert function, which takes some piece of data and says add that to the queue. There's a remove function, which returns whatever was at the head of the queue. And there might be some Boolean checks like is empty and is full that we can use to see if there's, you know, space left in the queue or if there's any data in the queue. All right, so here's our abstract interface, and again, the abstract data type means we just think of our queue in terms of these operations without worrying about how these things are made to happen. But just like with the stack, we have 2 immediate ways we can implement a queue in software. One is using a linked list, the other is using an array. So let's look at those, and let's begin with the linked list version. So imagine a Sentinel node. And we inserted a 40, and then we inserted a 20, and then we inserted a 100. We're simply going to store these in the list so that we keep track of all this information. But the way we're going to do this, we're going to add these numbers to the end of the list instead of the beginning. So we insert a 40, it's going to sit here. When we insert a 20, we're going to actually add that to the end of the list. And then when we insert a 100, we're going to add that to the end of the list. So we're doing this backwards from how we did a stack. So the tail of the queue is always out here at the end of the list, and the head of the queue is up here in the beginning. So when we say remove, we're just going to look at the head, the beginning of the list. That's the value that we're going to return. And we're going to want to delete it, so we'll just take the Sentinel, we'll point to whatever this head node was pointing to, and that removes the 40 from the list, and we return the 40. So the init function, that's just, you know, the same initialization for our stack, same initialization for our linked list. It just makes an empty linked list. The remove function is just return and delete the first node of the list. So we're just going to go to the first node in the very beginning, the thing the sentinel is pointing to. That's the value we're going to return from the remove function, and we're going to delete it from the list. So after we return the 40, our sentinel will point to the 20. And is empty is the same as with our stack, right? If our queue is empty, it means the sentinel's pointing to null. There's nothing in the list. So is empty is easy, and is full we're probably not going to implement when we're using a linked list, because the only time our queue becomes full is when the system is completely out of memory, and that's an abnormal situation. The insertion function is interesting though. So how do we insert a new piece of data like, the number n? Well, we want to add it to the end of the list, so we just go ahead and we start at the sentinel and we follow node to node until we get to the last node. In other words, we get to a node whose next field is null. We create our new node and we have that last node point to our new node. So really all we have to do is make a new node, add to the end of the list. But how do we get to the end of the list? If we start at the sentinel and we just follow from node to node to node, that will get us to the end of the list. But that's an order n operation. If we had a million things in our queue, we would have to do a million iterations of our loop until we got to that last node. And then we could make that last node point to our new node. And order n is inefficient. So what we can do is we can create a new variable. I'm going to call it tail pointer. And I'm always going to have tail pointer point to the last node of our list. And so I'm not going to just follow through from node to node to the end of the list. Here's how I'm going to insert a new node. I'm going to make a new node. I'll just assume it's called new node. And then I'm going to say tail pointer next equals new node, and then I'm going to set tail pointer equal to new node. So if I want to insert a 70, I'll create a new node with a 70 in it. I'll follow tail pointer to find the last node. I'll set its next field to point to the 70, and then I'll change tail pointer to point to the 70 also. So I've added a new node to the end of the list, and this was an order 1 operation. Took, a fixed set of steps regardless of how many pieces of data were in here. And things are set up for the next insert, because now my tail pointer points to that last node, which is a 70. Next time I want to insert something, I'll make a new node, follow tail pointer to here, point that thing to the new node, and adjust tail pointer. And to initialize, I just set tail pointer equal to the sentinel node. So initially my tail pointer points here, and when I first insert into an empty queue, tail pointer is sentinel, so sentinel next will point to our next node, our new node, and the new node will be what tail pointer points to. So that's a nice little embellishment to change us from order n to order 1. And those little wins are important, right? Those orders of complexity will add up over time. So using this tail pointer trick is a convenient one. And it's got to be a tail pointer. If we tried to put the tail here and the head over here, we would not be able to do this. And I'll let you think about why that is. What happens if we try to put a head pointer and put the head at the end of the list? What goes wrong with that? So that's a practice problem to work on. Alright, so just as with stacks, with queues we can also implement a queue using an array. And so let's picture an array here, and I'll draw the array sideways. And let's just suppose we have an array of 10 elements. So we'll just label the indexes. And maybe we'll call this array Q. So we've got an integer Q, bracket 10. And with our stack, we needed an index that we called a stack pointer to tell us where the top of the stack was. But here we're going to need a pair of indices, which I'll just call head and tail. And my init function will just be head equals tail equals 0. So head and tail will both point to the same element. We'll set them to 0, but as long as they point to the same element, that's an empty queue. And so when we want to insert, and remember we insert at the tail of the queue, so we're going to do something like this: Q bracket tail equals n. So we'll store our first piece of data here. So let's say insert, I don't know, let's insert a 50. So we'll store a 50 right here, and then we want to increment the tail. So tail will point over here. And then if we insert an 80, that would get stored at the new tail location, and our tail will point here. And let's insert 30. So we'll put a 30 here, and the tail is now pointing at this next location, index 3. So remove we want to remove from the head of the queue, so I'll just say r equals q bracket head, and then increment the head, and then return r. So the first time we call remove, we'll look at the head as a 50, we'll go ahead and return a 50, and we'll change the head to point right here. So now we're getting ready to remove a 30, an 80. And if at this point we insert a new value like 100, we would take the tail location, we'd store the 100 there, and we'd move the tail to point down here. So each time that we want to remove, we just look at where the head's pointing, that's the value we return, and we move the head down here. So that's our basic insert and remove operation, but there's some complications here. So the first complication is our queue empty? So how do we know our queue is empty? If the head and tail are equal to each other, then we want to return 1 saying, yes, the queue is empty. Otherwise, return 0 saying the queue is not empty. So empty queue is easy to detect. Anytime head and tail point to the same spot, there's nothing in the queue. But how do we know if the queue is full? Well, that's a little trickier. So we'll come back to that in a minute. But let's look at the insert and remove routines. Suppose I insert a few more pieces of data. So I put some data here, 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 here. And now my tail is pointing right here. And suppose I remove the 80 and the 30 and the 100 and all of these things, and I do all of these removes so that now my head is pointing right here. Alright, I only have one thing in my queue right now. That's this number right here. All of these things that got inserted, they also got removed. But if I just go ahead and I insert something here, like I insert some new piece of data, and I increment my tail is going to be equal to 10. It's going to be pointing past the end of my array. And that's going to cause, seg faults and data corruption and things like that. But my queue is not full. it's only got 2 pieces of data in it right now, this piece and that piece. All of these spaces are empty. What I'd really like to do is take my tail and wrap it back around and start using these spots in my array. So when I increment my tail, I should also add an extra statement in here, like if tail equals 10, then tail equals 0. Wrap it back around. And same thing when I'm doing removing. If I remove from the head, if I have my head pointing right here, and I remove from that location and I increment my head to be equal to 10, I should really wrap back around, because I know that after I inserted here, I inserted there. So if head equals 10, then head equals 0. And so one way to think about this is, as we can imagine, as a circular array. So instead of drawing our array as a simple pipe, we can think of it as something like this. Where this is element 0, 1, and so on. And when we insert things, we move down in this direction, and when we remove things, we move down in this direction. But after we insert at location 9, as long as this next location 0 is not in use, that's where we would insert the next thing. So that's what this rollover, this setting things back to 0 when they exceed 9, that's what this rollover is doing. And so this complicates our notion of when a queue is full. We can't simply say, hey, if the head is equal to 9, our queue is full. Because it's possible that our queue is only occupying these locations right here. And we've still got, plenty of space in our queue. So how do we know if our queue is full? We have to see how many things are in our queue. And we can do that with a little bit of fancy math on the head and the tail, but we could also do the following. If we were to insert something which increments the tail, would it then look like our queue was empty? Would incrementing the tail and possibly rolling it over make it equal to the head? So how do we know if our queue is full? If insert makes head equal to tail, then we're going to say the queue is full. So if doing one more insert would cause the tail to be equal to the head, we'll say our queue is full. And it's actually not. We actually have one spot left, but that makes it possible to easily say, hey, we've only got one space left, and we're just going to say that's when our queue is full. And if we really want to be able to store 10 things in our queue, just initialize your array to be 11 things instead of 10. But that's the easiest way. The other ways we can do it would be, setting flags, for example. So if we insert something, and after we insert the tail and queue are equal, tail and head are equal to each other, we can set a flag saying, okay, the queue's full right now. Don't allow anything else to be added to the queue. So there's different ways we can do that. But this rollover idea is important, and there's other ways we can do this. For example, instead of incrementing the tail and then setting it back to 0 if it's equal to 10, we could say tail equals tail plus 1 modulo 10. And so this increments, adds 1 to the current value, and if it's not equal to 10, it's just going to set tail equal to tail plus 1. But if tail was 9, tail plus 1 is 10, 10 modulo 10 is 0, tail will become 0. So we can use a modulo operator to make that automatic. So that's array-based implementation of a queue. A little more complex than a stack, but still basically the same idea. And you've got some practice problems you can use to work on those concepts. All right, and the last comment I want to make is just sort of a general notion of why are these structures important to us? Why do we care about stacks and queues? Stacks in particular are used all over the place in computer science. The most common application is when you make a function call. So we've got, say, a main program which is doing something, and then at some point we say make a call to some other function, and then our function says return, and we go back here. And then we do some more things, and maybe we make another call to that function. But this time when it says return, it comes back to this location. So anytime we want to call this function, yeah, we just have to jump to that location in memory and start executing those instructions. But the return statement goes back to a different location depending on where we were called from. So we have to save this return address somewhere so that the return instruction knows it should go here or it should go here. And where do we store that return instruction? Well, we could store it at some particular location in memory, but remember, we can nest our calls. So it's possible that while we're executing this function, it might make a call to some set of code, and that might make a call to some set of code, which returns here. And then maybe this makes a call to a different set of code, which returns here. And then eventually we return, and we need to return back to here. And then when we get to this return statement, we need to come back. So we might need to keep more than one return address. And the natural structure for this is a LIFO. When we make a call, we need to save this return address. That's the last return that we're going to make, though. If I make some calls in here and make some calls in there, the first return statement I have is not going to go back here. It's going to go back to the last thing that I saved. So when you make a call, you push the return address. And when we say return, we basically go to whatever address is at the top of the stack. We pop that off. So you can play around with that on paper and try to get an idea for how the stack is used to record these return addresses. And if you've done Engineering 270, or when you do Engineering 270, we talk about the stack and how it's used for calls and returns, and we talk about the push and pop instruction, and those are all related. And so the stack is critically used in most architectures to store return addresses so that we can make a series of nested calls and then get back to where we were and do these things in the right order. Queues, on the other hand, are used anytime we want to queue up, requests for something. So for example, maybe you have a printer and you've got different jobs that are executing, maybe different users on a shared system, and each of them at some point in time wants to use the printer. Well, when you print on a shared computer system, you don't directly start talking to the physical printer. What you do is you take the information you want to print and you send it into, guess what? You send it into a queue. And so there's this queue, and so this is printing A and printing B and printing C. So A goes into the queue, and then B, and then C. And the printer looks at this queue, and when it sees something in there, it starts printing. And when it finishes printing A, it removes it from the queue, and if there's anything else in the queue, it'll start printing that. And maybe while it's printing B, another user says, I want to print D. Well, D doesn't start getting set to the printer. It gets sent into the queue. And when the printer finishes with B, it'll print C. And when it finishes with C, it'll print D. So anytime that we have, sort of a shared resource, and we want to deal with things in order, they're handled by a queue. Right? Your email, in some sense, is set up in a queue, where messages come in and they get lined up in a pile, right? And if you're reading from oldest to newest, you're working with a queue. If you're reading from newest to oldest, you're working with a stack, right? You might have 500 emails in your inbox, but the email that you just got, that's the one that's sitting, at the front of your email list, that might be the first one that you read. And that's a good example of the difference between stacks and queues. If we treat that as a stack, we're always reading the most recent email. Unless we, sit down and read 500 emails, that oldest email, we're never going to get to it. Right? And maybe that's good. Maybe we just want to deal with the most recent things first, and the older things we just don't get to. Or maybe we want to make sure that we deal with everything, so we want to use a queue. We want to make sure the first email that we received 2 years ago is the next one that we're going to deal with. So these things pop up in everyday life, but they also pop up in computers. And when we start working with binary trees in a few lectures, we'll see good applications for stacks and queues. And stacks are going to turn out to be absolutely critical for doing recursion and recursive functions. Primarily because recursion involves, making function calls to ourself, but still function calls. And anytime we do calls and returns, we're working with a stack-based structure. All right, so that's an overview of stacks and queues. Thanks. See you next time.